Thanks for joining on this talk. I'd like to thank Magda at CSA Global for actually putting me up for this, and also to Helen and Tim at SGEG for guiding me through this virtual process. It's a bit sort of daunting sometimes, but we're here now. So I guess ore control and geometallurgy aren't really new ideas, but I talked to a lot of people about it, and they all seem to have different sort of feelings about it, different ideas as to what it actually is, and all quite different, but not. So I'm hoping this talk might explain in layman's terms what the concepts of ore control, geometallurgy are, and why we should be broadening our horizons to use these tools as part of our everyday exploration and mining activities. So I just wanted to set the scenario first up. For economic efficiency, seeing as that's part of the title, let's say we've got a 600,000 tonne gold deposit. At 2 grams per tonne at approximately 38,600 ounces on today's rough price for gold, that's probably worth $77 million. But if we were to drop that grade by 0.1 gram per tonne, we would lose nearly $4 million somewhere, whether it's out in the tailings or whether it was never there or it's gone to the waste dump. 0.2, we'd lose nearly $8 million. Just even losing 0.05 gram per tonne gold is nearly $2 million revenue that could have been saved if we'd been a little bit more efficient in our mining, or if we had more accurately determined our resource. Whatever reason, it's easy to see that a slight change in things like grade can make quite a significant difference in terms of the economy. Similarly with tonnes, if we go back to our 600,000 tonne gold deposit, tonnes is volume by density. So people always seem to be very good about estimating their volumes. A lot of people do not pay much attention to density, which is interesting because we spent all our money on trying to get all the grade correct and not so much on the tonnes, and yet metal content is tonnes by grade. So I just wanted to demonstrate the effect of, just changing 0.1 density value. You have similarly the same sort of things at $2,000 per tonne gold. Basically, you'd be losing $130 a tonne every time you lose a 0.1 in density. And particularly in Western Australia, where a lot of our ore bodies start out in extremely weathered zones where the density is highly variable, it's very critical to ensure that we get an adequate amount of information to really tie that down. So it pays to get it right. And by estimating grains and tonnes, and you can increase your efficiency and maximize your potential profit, which is really the increased economics. That was just sort of setting the stage at the sorts of things that, that can go wrong or right, because, if you get an extra 0.1 gram per tonne gold, of course, that's a really good thing. But the point is that we need to actually pay attention to the details and carry that through right from the start during exploration phases. So just setting the stage again, what is sustainability? Well, the Oxford Dictionary says that it's the property of being environmentally sustainable, the degree to which the process or enterprise is able to be maintained or continued while avoiding the long-term depletion of natural resources. And that's kind of where most people seem to think it is today. It's really, largely to do with the environment. In actual fact, the concept does come from forestry as way back as in the 19th century. But in the purest sense of the word, it comes from the Latin meaning to hold, keep, or support. And it's in that context that I'm going to be sort of really referring to sustainability. It's going to be like the ability to maintain and support ongoing processes during the life of mine chain. So just as figure 1 from the JORC code basically confirms this part of sustainability as a concept of maintenance support. The ESG part of the sustainability, the environment, social and governments, will by default be a consideration with better ore control, but we're not going to discuss that here. That's a whole new sort of whole big topic for another day. So from the overall concept, how sustainability can be maintained by maximizing the economics of the life of mine cycle, and we do that by improving efficiency. The ability to increase efficiency will arise from education, and the education is achieved by following the concept of ore body knowledge, where geometallurgy can be used to identify and classify those physical and geochemical properties of the rocks that are going to impact on product recovery, which to my mind is really the ultimate goal. And the way by achieving this is by an appropriate ore control model. So what is exactly ore body knowledge? I guess it's focuses on the integration of geology and mining and metallurgical, environmental and economic information at an early stage of the life of mine to create geologically based predictive models for mineral exploitation. Well, that's what Google says. It's comprehensive knowledge and understanding of element and mineral behavior. And we think we might have it, when we start out, but in actual fact, there's quite a big missing link, and it's all about looking at the physical properties of the minerals and the ore that we're dealing with and how that is going to impact on the final product, which is recoverable product at the end of the life of mine. So the geometallurgical input, it's not just a significant contribution to ore body knowledge, it really is the critical contribution to total ore body knowledge, because it can enable the development of strategies along the life of mine to mitigate the risk of variability in the mining operation. Geometallurgy, it's the integration of the geological, mining, metallurgical, environmental, and economic information to maximize the net present value of an ore body while minimizing technical and operation risk. And that's what Google says. This is the one thing that everybody has opinion, and the meaning is different depending on who you are. If you're corporate, it's about the other information necessary to successfully convert grade tons from out of the ground through the process plant and out the other end to a value-added product. If you're talking to a metallurgist or a process engineer, it's the information that will ensure the minimum amount of ore that might find its way to the waste dump or tailings dam. A mine geologist might say it's the recognition and identification of the physical properties of the ore and how these properties impact product recovery. The exploration geologist is all about the 3D model that describes the alteration and mineralogical domains for potential ore type definition. And a very wise metallurgist once said to me, if you manage the bad stuff, the good stuff tends to look after itself. And that's kind of where I have sort of arrived at a place where I've recognized that by paying attention to the things that are likely to impact negatively on product recovery, you actually optimize the good stuff that's going through. And that's the trend that I think we should follow. So really, the ore control is a solution to successful process circuit design, control optimization, and problem solving in a global sort of sense. But to really understand where it all fits in, we need to just look at the life of mine as a whole. So ore bodies are generally very variable in terms of grade and density, mineralogy, alteration, weathering. Most companies spend millions of dollars doing exploration to define this resource with close-space drilling, thousands of assay samples, and that certainly gives greater confidence in the grade numbers. Little thought's often given at this stage to a geometallurgical assessment, which would assist in defining the downstream processes of extraction of the metal. And even the mining procedures mightn't even be considered at this stage. And the problem is that grade, density, mineralogical variability results in extremes in metallurgical response. And of course, that provides a source of uncertainty that will affect mine design and plant design and capital investment decisions. So I've been sort of thinking that why don't we spend some of the money that we spend on drilling grade at the very early stages and use some of that on geometallurgical sampling and get a bigger picture? And some people are starting to do that already. Other people, it's traditionally, that's not the way to go. And so it's trying to sort of broaden people's outlook, thinking a bit laterally, taking the total ore body knowledge approach to gather as much information about the ore body at a much earlier stage, because that will diminish the risk further on down the track. So with our life of mine, we basically have our exploration. We then move to resources. We'll do reserves, mine planning, mining and processing. And it's sort of like this big circle. Basically, exploration, resources and reserves are sort of one part of the operation. And often people are involved in this that will never get to this stage here. And vice versa, the people that are working in the mining side of things or the processing side really don't have a great understanding of what's gone on in the exploration and the resources. So if we're lucky and we generate a resource and we see how much of that gets converted to reserves, we can get to do some serious mine planning. And at this stage, the focus is always on grade. And that makes sense, because if we don't have the grade, then we don't have an ore body. Prior to processing, we might do some large-scale bulk metallurgical test work around about here to see what processing route we go down. But it's in a very short time, we've gone for extreme lot of detail here to a lot of bulking down here and not much in between here. But I'm suggesting if we was to really, at this stage, change our focus to not just to grade, but also to recoverable product at the back end, that will give us an opportunity or a scope to actually understand at a much earlier stage the types of things that are going to affect how much grade we can dig out of the ground and put through the plant and get out the back end. So, which I've just said there. So if we basically take our thinking and just encompass the whole life of mine cycle rather than just each individual area, it allows the opportunity to minimize the effect of negative parameters on 100% recovery. And then, of course, that by definition will improve efficiency through the whole life of mine cycle. That has to increase economy and then generate longer term sustainability. So just my definition of sort of recoverable product, looking it up online, there's several definitions. It's the amount of valuable metal in the ore that's recovered by metallurgical treatment. It's usually associated with the latter part of the life of mine cycle. And the recovery factor in the plant is the mass of product recovered divided by the mass of the feed into the plant. And that recovery factor is really the thing that we're trying to optimize by doing early stage geometallurgical sampling. I like to think of recoverable product in a more simple terms. It's really to deal with it from the front end. You can think about it as grade times tons by recovery factor. Or if we're getting a little bit detailed here, it's grade times volume times density by recovery factor. And generally, this is where we start to go downhill almost immediately, because we've spent an awful lot of time and effort into estimating grade to a great degree. Volume is generally estimated pretty well as well. Density is another thing altogether. Not a lot of people spend sufficient time and money accumulating enough density data to minimize the variability of the deposit. Excuse me. So with the whole concept of geometallurgy, we can think about the fact that grade, mineralogy, and rock mineral textures are variably distributed across the mineral deposit. This natural variability does have a direct sort of control on the metallurgical performance of the ore feed, and which is obviously a function of mineralogy, grade, whatever process you use. If it's not spatially quantified, then we've got an increased project risk, and then there's a potential for losing revenue through reduced net present value. There's constant pressure on mines always to improve efficiencies and reduce costs, and this often could be avoided if sufficient geomet info had been available at an early stage to better characterize the ore. And that is really the whole point of geometallurgy, is to obtain a better characterization of the ore and waste that's going to go into the plant or not. So generally, when I said before, we will do metallurgical test work at a fairly late stage in the life of mine cycle. It will be like bulk samples, blended. It's a traditional place for where the test work does begin. Then it might ramp up to a pilot plant stage with commissioning, and do some large scale met testing through that process. But if we were to start a lot earlier, during the exploration stage and resources stage, we'll be doing small scale localized variability samples across the deposit to get a representation of what the physical variability is going to be prior to actually designing the plant or even the mine. So the important thing is to understand the link between the geology, mineralogy, and metallurgical performance. And that's done by detailed domain characterization, and that provides an opportunity to predict ore behavior during the mining and processing from the test results that you get back from the geomet sampling. And the physical behavior of the minerals is related to the mineralogy, and it also includes gangue, textures, target minerals. There's a whole lot of stuff that can actually go into this geomet sampling, which is obviously targeted to the specific commodity in mind. But the principle is that you treat the results from that in a similar statistical way as you would grade or density or geology, if you're modeling geology as an interpretive thing. And basically you'll end up with a block model that will have, on a block by block basis, not just grade and not just a geological code, but all the physical properties, and as much as dollar value or reagent costs or deleterious minerals. There's so much stuff that can go into a geomet model. It's not funny. And all of this can be got at a much earlier stage. Now, one of the key things is to getting this information is to have a really good suite of multi-element geochemistry at the start. And I sort of tend to suggest to clients that in your early stages, once you've decided you've got something that you want to drill out, that's the stage, your first phase of drilling and your second phase of drilling, which is generally wide spaced, is use that as your multi-element geochem to start with, so that you can actually get a very quick idea of where your domaining is likely to go. And then it's up to you to sort of decide how much more you want to do, but it's not excess money. It's what I call preventative maintenance money. It's only a small cost of the entire drilling, and I would suggest strongly that when we first start out, that we don't make assumptions about the elements that we're going to need. There is just basically do the lot, see what you've got, and then make the decision as to what assays to drop off for the closest spaced resource style drilling. So this variability sampling for geomet is to define the variability of grade, lithology, mineralogy, alteration, which we often do anyway. When we're doing our, modeling from sample populations from geochemistry. The key thing is to get a spatial distribution across the ore body. which means that you need to incorporate high grade and low grade samples, waste, enough to get statistical robustness so that you've got a pretty decent sort of idea of you know, what your histogram for your geomet sampling would look like. Some of the problems is that you get poor grade distribution. You often get a limited grade selection that weighted to the higher grades, which is good for averaging metallurgical performance, but it's not good for managing the sensitivity of performance to changes in grade. Often you might get too few samples, which doesn't lead to statistical robustness, or you might just not get enough of the elements assayed, and that will only give you a partial picture of what will occur in the treatment process, because you don't know what you'll get or you'll need. So a key point I think to take away here is, when you're first starting out, is don't assume, just basically see what you've got from a multi-element sort of suite, and then make informed decisions on moving forward as to what assays are going to be significant in your particular case. You just need to remember that blending reduces variability. So if we're bulking things together too early, then we have lost the opportunity to build sensitivity into managing further down the track. So sample as early as possible. You need multi-element geochem, accumulate as much qualitative and quantitative geomet data that you can. The critical things that affect product recovery are things like mineralogy, alteration, the effect of weathering on both of those, density, and the outcome will be a spatial 3D model which defines these geomet domains to pinpoint where to sample. And this is just to show you a case study. It's actually for gold. The multi-element lithogeochem approach was used in a geometallurgical sense to define the domains based on various element and element ratios. And so you can see that, you know, all these various lithologies were quite well domained at the end of the exercise. This is just a very quick sort of demonstration as to how to build up your matrix for sampling for geomet. I've just done it in a very simple stage. Say that we've got a body here with different lithologies, and we've got our weathering stamped on top of that. In a simple world, this is really what happens. You've got, say, 4 lithologies, you've got 3 regolith domains. All of these are likely to have, all of these ones from A1 to A3, D1 to D3, are what I would call potential material types. And they are all going to have differing physical properties, different metallurgical responses based on where they are located in space, either in a different lithology or a different sort of weathering domain. So what we've done here is we have assumed that in lithology 2, whatever it is, that we have ore in oxide transition and fresh, but in lith 3, we only have ore in oxide and transition. So moving forward to that, the geomet domain is what I would call, this is what we call the material types. So then we would choose these material types first up to sample for ore, but we would also sample the rest of these as waste, because we don't know how the input of waste into this ore body is going to affect product recovery. What we do know is that we will be putting waste to the plant because it's inevitable. So we need to make sure that we understand what the effects of putting waste material are into our ore. So this is when we can then decide, we now have all these material types. We have 1, 2, 3, 4, 5, 6 ore types, a few more waste types. We have decided that the geometallurgical sampling has decided that the metallurgical responses for B1, B2, B3 are very similar. So we can sort of lump them all in together into one ore type. We've decided that B2A, which might be an alteration zone in a fault zone or a shear zone and has a different metallurgical response, we need to keep that separate. And then we can bulk all the waste together as, 3 types of waste as well. Density needs to be represented over the entire deposit as well, statistically covering all potential material and waste types. Moisture content needs to be measured at all times, and then one of either in situ density and or dry bulk density, and then you convert the other. And you need both, because when you're mining, it's in situ density, it's wet density that's actually measured when you're measuring truck tons. And of course, dry bulk density is used for when we're reporting resources. So if we want to sort of manage our mining and have arguments with our contractors when they're telling us that they've actually picked up more than they have, you need your in situ wet density. Now, hyperspectral mineralogy is another big tool of geomet sampling, and it's used to define regolith and weathering boundaries. And this is an example of one where this was worked very successfully to define an upper oxide zone, a lower saprolite zone, a transition and a fresh zone. And the interesting thing was that when you actually logged that back to the original historical logging that had qualitative assessments of weathering down the hole, that they matched up extremely well with that. So geomet complements but doesn't replace traditional metallurgy, but it just gives you the heads up at a much earlier stage. Basically, we have primary variables, which are things like rock mass and density, metal grade, grain size alteration, redox zones. These can all be measured directly. Things like ore recovery and grindability, particle density are all things which are estimated by predictive models from primary variables. All of these things can go into an ore control model. And this shows you sort of roughly how the program can be implemented early at the exploration stage. You can measure primary variables, calculate your responsive variables. That gives you some very good processing information. Build your geomet model and ore control model, and then put it into the block model, which is the ore control model. And then that gives you a really good tool for first pass plant design and production forecasts. And really the only difference between a geomet sample and a metallurgical sample is size. So we've got small scale variability in geomet sampling. This helps you identify material types. Metallurgy is large scale or bulk sampling, and it's more like along the lines of the pilot plant test work, and it basically will be done on your ore types. So the feed for the ore control model from geomet sampling is a spatial 3D modeling of your domains. And then you can use geostatistical or multi-element regression predictive techniques to find a connection between your predicted grade geochemistry and your geomet parameters, which could be things like recovery, upgrade, mass recoveries, acid consumption, acid mine drainage. All of that can be related back to your grade block model. So just ore control is the tool by which you can do this. Its foundation is based on geomet domaining and subsequently identified material and waste types. We're assuming that these material types have been representatively sampled across the deposit for small scale variability characteristics. And there's many ways to predict models into an ore control. You can find one that's just suitable, that works with the data that you have. And an informative ore control model is the solution to successful process circuit design. So I wanted to sort of just go through and give a practical example of how ore control could be used. And I'm picking sort of nickel laterites because they're really complex in many, many ways in terms of their processing requirements. They have really sort of complex mineralogy. They have, because of the degrees of weathering there, they're there's more than one sort of ore type that requires sort of processing, and depending on what the composition of the weathering profile is depends on what type of extraction process you might use. And no one nickel laterite is the same. So it's sort of an interesting sort of comparison, because each one does have its own unique geological and mineralogical characteristics, and they need to be recognised and understood from a geomet perspective, because the success of nickel laterites is really totally based on the appropriate delivery of various ore types to the plant, depending on what sort of processing has been selected for it. The two examples in Western Australia, for example, are Murrin and Ravensthorpe, and they're both quite different. Murrin has a pressured acid leach system and a heap leach as their processing options. Ravensthorpe has a beneficiation step where, because it's high in silica, so it enables a lot of it to be crushed and ground and liberated in that way. The limonite ore goes into a high pressure acid leach, which has a high recovery, and then the saprolite ore is just put on atmospheric leach. Both of which are really complex. Both need to manage acid consumption, sulfur, and a lot of other things. So the composition of laterite ore is the key to how it's processed and consumed. You can upgrade nickel from 1 to 4% to concentrates with grades 10 to 20%. The ore control is ideally a combination of using the resource block model and the geomet model to come up with predictive equations for identifying things like the nickel recovery and nickel upgrade and other elements like magnesium and iron that have impact on the recovery of the nickel out the back end. Mine planning ore control would also include metallurgical updates and plant scale-up factors. So there's an awful lot of information that's required to sort of really control what's going on there, such as these factors that I've just been speaking about. Well, one thing that's notable, certainly with nickel laterites, and I haven't really sort of studied them much in other commodities, but with predictive models can be created at specific sort of P80 grind sizes. And if you decide to change that, then you'll need to sort of have a different set of predictive models, because as you sort of increase your grain size or decrease your grain size, the elements sort of involved that might be sort of having an effect on product recovery, the proportions of that will change. And so you can actually then have several different predictive models for the one commodity at different cut sizes, so that if that happens to the plant, you can basically monitor that and just monitor better how your recoveries are going up and down based on the sizing of what's passing through the plant. So sort of in summary, we want to sort of deal with the concept of total ore body knowledge, which is really gaining as much knowledge as you can about the ore concerned, which will involve not just grade, but also all about the physical properties of the minerals and the waste minerals that it's in, that's going to affect the end product, which is total recoverable product. And if we focus on that at a very early stage, then the understanding of why we need to do geomet test work at an early stage does tend to become a bit of a no-brainer. So we can build on the latest resource model by finding relationships with interpolated geochem to define those geomet parameters. That's because that's the most detailed basis upon which to build the ore control model is your interpolated grade model. So you use statistical determinations to build the predictive models, and your ore control model is dynamic, so it can change with any way you like. It's used for mine planning. It can be used for ore markout based on appropriate parameters such as recoverable product, even NPV or dollar block value. In fact, not just grade, because I'm hoping you can sort of see that grade is only just one part of the equation here. It's certainly the important initial part, as I said, because if you don't have grade, you don't have an ore body. But the whole focus should, once you've got a deposit, is the focus should be on understanding how you can actually approach getting 100% of that grade out of the ground. And we know that we won't, but the whole point will be to attempt to optimize that sort of recovery as much as possible. Minimize risk at an early stage, maximize efficiency in mining and processing, increase profitability, you get better control, better economy, maintain sustainability in every sense of the word. And this is basically what the whole concept of geomet and ore control, to my mind, has got the opportunity to provide. So at the end of the day, there's one recommendation that I do have for everybody, is that, you know, all these sort of departments here often operate in a type of silo scenario, in that everybody's always so busy. Exploration doesn't really talk to the resource geos, and they don't even probably talk to the reserve, you know, the mining geos when they're doing reserves. But if you can find somebody in your company or yourself that has an overall understanding of the connection between all these departments in the life of mine cycle, cross-department communication is a critical key to success with ore control. You need to be able to sort of communicate with each other in departments so that everybody understands that you're all on the same path. Thank you. That's it.